So when you're doing solid state, it's cool that it's a hot topic. Catalysis is now more important than ever. Alternative energy, you're going to get great jobs. One problem is that as children, you're thought to think very spatially. And when you start learning about atomic orbitals, hydrogen, S and P and all that, you cannot think that way for material science. You have to have a completely different way of thinking about electronic states. I'm going to start covering that today. Now, for most quantum classes, this is a blip. Most P-Chem people study molecules. P-Chem people studying materials is kind of on the newer side of the spectrum. And so awesome. So for people who study materials, today's lecture is absolutely crucial. So it goes from being like kind of this nice exercise to help you get to understand quantum to, by the way, this is how you do quantum mechanics, and so that's like really important. And for all of you, remember, professionally, sometimes I do sit down and solve wave functions, sometimes. And I am going to show you how I do that. For the most part, you don't, but it's all about changing your way of thinking. Anyway, now one thing that's also horribly important is I'm a little concerned that you guys are still a little bit flummoxed about X, right? So I'll give you an example. Let's write this. Okay, and this is like, now we know that this is a point on a wave function. And let's say that that's position 5.0. And so this point is this right here. And so if x is the 5.0 ket and dx is 0.1, then this is the 5.1 ket. So what this is a translation. It's taking this value here and it's moving it over here to 5.1. Right? So that's what this does. Why would you want to do that? Really no reason. It's good practice, it's good math skills. We talked about proving what the momentum operator was last time. You don't really need to do that. It's all about practice. But in terms of your ability to think about this correctly, I'm hoping that you're okay with this kind of stuff. Because if this is 5.1 still, if what you're trying to do is represent the wave function at position 5.1, these are the same thing. You just got to recognize that this is, dx is still a 0.1, so this is 5.0. 5.0 being shifted over to 5.1. Either does that, just make sure you get it straight. Actually, you don't have to keep anything straight, right? dx is still a small number. There's really nothing to this. So anyway, that was important. Let's see, there was also the fact that this can be recast. The one reason I wanted to do this was, where am I at? Where am I at my own work? Sorry, have I gotten lost? No, yeah, right there. What do I want to do? Oh, yeah, okay. Sorry, yeah, here we go. I thought I was a little bit better prepared. Okay, this is, so when I was reviewing my notes, stuff I had from when I was a grad student, plus the book, you see this, and you're like, man, what the heck? This is this? I mean, how? And again, it ends up being really, really easy. So if you're at, what was this a minute ago? This was 5.1, right? So this is position 5.1. So remember, this is the wave function at our starting point here, right? So in the way I define this is position 5.1. And what I'm doing is I'm subtracting I'm going to fit the wave function to a line. It has a slope. And so this is like the intercept, and this is the slope times delta x. M delta x plus b. Right? And so this puts me, again, from here to here. So, yeah, I just fit a line. Now, the thing is, this wave function is a Gaussian. It's not very linear. But again, I've exaggerated it, right? 5.0 to 5.1. dx is infinitely small. Any 2 points can be fit by a line. And if these 2 points are right next to each other because dx is so small, a line connects them. So this is totally fine. Anyway, so the thing is that, like as you probably jumped, as I jumped when I first saw this, I see this and I kind of get this, and then I see this and I'm like, and this is just a smorgasbord of stuff. But then again, we take our time, a slope, which is m, delta x, literally delta x, plus b. Plus, I guess the slope has a minus sign, whatever, doesn't matter. Slope is negative anyway. So, okay, just want to remind you of that. Let's see. What I wanted to do, and also in terms of review, let me do let's write something in Dirac notation and figure it out. Okay, now I'm looking at this, and what I'm seeing is a momentum operator operating on state alpha being projected into state beta. Again, you should be able to read Dirac notation well enough to know that. Now, you also had undergrad quantum, and you know that expectation values, which are, I mean, clearly this is an expectation value because we've gone over that, but it also has that look from our undergrad, where you take a wave function complex conjugate operator wave function. I can just tell that I have two different types of wave functions in this case. So I need to find that representation here. And again, this is just some practice to make sure that our Dirac notation with dx is good. And there's some homework problems. And my point to you here, in light of what I said a minute ago, you've got to be solid with this, because here's what I'm going to do at the end of the lecture. I'm not going to be dealing with x's, I'm dealing with p's. Solid state quantum is not done spatially, it's done with momentum, not x. And get this, all right, so I've been bragging about, again, this is basically a wave function. I know it's a detail that it really represents a point on a wave function. This is really easy to understand, right? It's that. I mean, how hard is this, right? This is the wave function, here's an x. This is not hard to understand. What happens when that's p instead? It's a little harder to understand because we just don't think that way, but you have to. The other thing is to understand that if I represent this instead of x as p, it's the exact same information. There's nothing lost, there's nothing diminished about doing quantum mechanics with momentum. Nature thinks in momentum, not in position. We think it's position because our experiences are skewed. Okay, anyway, so there's this. Now imagine this is, at some point I have to have an exam too, so we'll just have 2 exams in the final. Final, I'll have all computational. The next exam, I'm going to have, I mean, there's not much computational, there's not much MATLAB I can do on this, so I'm just going to throw some Dirac notation and have you work it. Now, anytime I see this, resolve an identity. That's the thing I like about Dirac, is that whenever there's a problem, there's always a good idea of what to do first. Add an identity. Let's do that. Okay, so, and bookkeeping, I'll put a dash, and you'll see why in a minute. It's all just a matter of bookkeeping. Okay, now again, identities can be inserted pretty much anywhere, but you have to be careful. The only thing you can't do is take the inner product, outer product. You can't take the outer product and break it up. Under some circumstances you can. So anyway, so there's the number 1. Of course, I inserted it here, so here's my P. And here's alpha. Okay, cool. All right, now I recognize that. Remember, it's a point, but integrals are like scan. They're sums, so this is like scan. Whenever I see an integral, I'm always thinking I'm scanning over the axis. That just pops in my head. And that's why this looks more like a wave function now. This is the wave function at a point, but I'm looking over the whole points, scanning over the points, and that's how I make a graph, right? So now I can kind of see the wave function in here. But it's also a complex conjugate because the x is on the wrong side. So that's a complex conjugate of, let me write that down. But before I do that, you know what? I'm stuck here. Now remember, I was telling you I was trying to get this looking like wave functions, and I've got a complex conjugate of the beta state. The beta wave complex conjugate of the beta wave functions right here, but this is still a bloody mess. Okay, now the trick here is to do 2 resolutions of the identity. So this is the complex conjugate of the beta state. Then I've got, so notice I am really starting to play serious crazy games with my mixing traditional type of quantum notation, undergrad type quantum notation, traditional chemistry quantum notation, and slipping in some Dirac notation. So I'm mixing it all up. Okay, there's my alpha wave function, cool. So that's nice. So I've got 2 wave functions now. Now I gotta just figure out how to deal with XPX. Now what we had done last time, and I meant to write this down, this is one of my review items I forgot. I had a separate set of notes that these are my review notes, and so sorry about that. One of the things we talked about last time is that the momentum operator acting on a ket is a very funky looking thing. It doesn't really reveal itself like we're used to, but if you act on a state and then project onto the x-axis, and notice how highfalutin and fancy my descriptors are. It sounds very, very scientific the way the words I'm using, right? Okay, so what I've got here is, okay, wave function, anyway, complex conjugate. Okay, I've got, it doesn't matter where I put, I'm gonna, I, H bar, remind you that those are, okay, I've got a delta function though. Sorry, I'm jumping ahead. And then we recognize that as, and I've got all my partials. Okay, now I know that this looks kind of like a little scary because I've got a derivative and some stuff, but first things first, that's a direct delta function. Right? Again, something that you should just jump when you see, but you know, on the take home or whatever. Well, it's easy. Our exams are take home. I'll put identities on them just in case. All right. Now, of course, what happens in delta, I love delta functions because one of my integrals is gone. I hate integrals. I hate double integrals, but one of them's gone now. And then I have to decide which one to get rid of. Let me check out my own notes to make sure I know. Okay, I'm going to get rid of the x double prime. And again, I'm sure that there's a convention about which one is which. But I also know it doesn't matter. I'm going to get rid of this one. And if I'm going to get rid of the double x, the x dash dash one, that means all the x dash dashes are now x dash, and that's that. I'm doing that. Okay, so now what do we got? I've got the complex conjugate. I've got I, h bar, dx, and all of the minus.
Yeah,
that was my question.
Right, minus. Yeah, sorry, just, right. Remember, actually, when I filmed last video, remember I made a minus mistake there too? Sorry about that, I fixed my notes. I actually wrote, I had little words appear in the board saying, oops, I'm missing a minus. Sometimes I'll try to digitally overwrite those mistakes, But I realized that because later when I caught myself, I couldn't really do that. I had to just let it go. Anyway, so again, wherever I see an x double dash, I write an x dash. And I should keep that here. Well, and I wrote the star right. Yeah, there you go. Again, just like we learned in undergrad, an expectation value is the integral of a wave function operator, and then the complex conjugate of the wave function. We're doing something a little bit more advanced here, that we're actually taking the result of this operation, and we're integrating that with another state, which is to project the alpha, the operated on alpha into beta. Now, why would you do this? I have no idea. Why would you do this? I don't know. I know it's happening. I'm querying the alpha state, and if it's an eigenvalue, if it's an eigenstate of momentum, then the state itself is unharmed by taking the derivative, and then I'm integrating that state times this other state, and I have no idea why I would do that, but I know that this is how it's done. I bet that if I'm doing some complex proof that you run into things like this, and as usual, a lot of this again is all just a matter of practice. I just want to make sure that you can hack your Dirac notation when it comes to x, because now we're going to p. Now we're going to go to momentum representation. One of those, again, the important thing is, here's repeating, is momentum representations of wave functions are as information rich. They have the same information content as a wave function in x. And when it comes to solid state electronic structure, because I have no way to calculate or visualize spatial wave functions with 10 to the 20 atoms, I have to do it with momentum. And I'll tell you a little bit more about that. So here's, and I'll use a little bit of the book. Okay, to start, how do I turn this into this? And this is how we tend to write. That's like the new psi for momentum. How do I do that? It's akin to turning an x state to a p state. Okay. Okay, so I'm going to show you how you figure this out. All right, so we're going to start with let's start with state alpha, particle in a box state, whatever. It is the highest occupied molecular. It's the band. It's the highest energy occupied band of a semiconductor. That's what it is. Why not? That's what this is. Electron in a band of a semiconductor. Okay, now what? Okay, I'm going to resolve an identity, but I'm going to do it in P. So, again, P is continuous, momentum is continuous. So I've resolved an identity. Okay, so I got to remind myself. Okay, so I don't know what to do with this. So what I'm going to do is I'm going to resolve another identity in X. So X dp, and let me make sure. Okay, I'm going to put that here. I have to think about where this was. And now I'm seeing the thing that I need. Okay. Right now, so this is like it, but so what, right? I mean, there's also some identities, but let's kind of walk our way through it. When I did this, I am basically, remember, so this is the wave function. It's a momentum type wave function at a certain momentum, but this means I'm scanning it over the momentum states. And here's another thing I wanted to point out to you, and you're going to be doing this. Let me draw my favorite Gaussian wave function in X. I'll make it kind of narrow. What we're doing right now, by the way, why did I do that twice? That doesn't make sense. I don't need to write it twice. Okay, as we are figuring out right now, a wave function, this is like something that comes up all the time, even in my own professional life. Little bell-shaped wave function, there's lots of little bell-shaped wave functions. Many things are bell-shaped wave functions. When I Fourier transform that, I just gave it away, when I do the necessary operation to turn it to the momentum representation, it's still bell-shaped. If it's thin, it comes out wider. If this is wider, it'll come out thinner. That's just a little, just note that. Anyway, that's what we're figuring out how to do. Okay, now again, this guy is like this one. So I've represented this, but notice what I've done is that I've projected that into x, basically, right? So here is, here's basically this is a point on this, and then I'm projecting that to the position representation. And this is my translation factor. So I need to know this. Now, another heads up I need to give you. I know I said this, and it looks like I'm doing the opposite. I'm actually going from here to here. That's because it's like a better way to solve it. Like in all things, there are sometimes I do some steps, add a Jacobian, I don't know why, because guess what? In 2 steps, I'm going to have a really nice easy solution, although you don't see it yet. So anyway, that's why I'm doing it this way. Now here's a little bit of an aside. I just wanted, I know this is like looking a little bit foreign here. Again, just want to point out that I'm just taking this momentum type wave function and I'm sliding it into an x representation. But to make this more clear, none of these really make a lot of sense until you have a bra. I always need a bra. So let me rewrite that. This isn't in your book. This is something I figured out that you could add that makes this a heck of a lot more clear. And so then I've got x prime and an x, and so now I've got a delta function. Then I've got x and p, which is what we're looking for. This is the point of this lecture, is to figure this out. This is the thing that allows me to switch between x and p and x. Okay, and again, this is a delta function. So now I can get rid of my x wave function. And again, remember, so one reason I'm writing this is definitely, right, we know that this is a point on this graph, but again, this is very easy for us to interpret. And now what? Now what? So now I can get rid of, what do I do? Everywhere, I think about what I'm doing. Oh, okay. When I get confused about what am I doing, about how do I treat the delta function? All right, for one, I am erasing I'm erasing one of the integrals. One of the integrals is killed off by the delta function. It's the x integral. That's now gone. But remember, I'm always telling you, like, okay, wait, am I getting all the x dashes and turning them into x, or am I turning all the x's into x dashes? And you got to make sure you keep it straight. You could do either, but you got to keep it straight. And I realize if I'm getting rid of dx no dash, that means all of the x's turn into x dash. That's how you do that. So this ends up being, so this is wiped out, and this ends up being, okay. So again, this thing is our spatial representation that we're very familiar and comfortable with, I hope. Here's the thing we're starting to learn. Here's the momentum representation. And here is how we turn one into the other. And again, I know there's a lot of dashes on the x's, and that's weird, but they don't really matter. Okay, so if you give me if I give you a momentum wave function, once we know what this is, we can turn it into a x wave function from psi of p to psi of x. So this is how we do it. So again, this is why we're looking for this. And the dashes are not dash, doesn't mean anything. It's not important at all. Okay, so anyway, I just want to put that out. Okay, now this is all, let me move this up here. I'll keep working down this way. And again, I cannot emphasize how important this lecture is for material science. Like how I drew that narrow wave function into a wider wave function. That is a little mental calculus that goes on all the time in my head because I'm a materials guy, right? Okay, now how do you solve? So we're looking for x or x dash of p, doesn't matter. How do we do that? Okay. First thing is, there's no magic here. Remember, an operator times its eigenvalue. An operator times its eigenstate, eigenket, gives an eigenvalue, and the state comes back. This is exactly what we've been doing the whole time. Let me project x onto that. It's like I did a minute ago. This is a number, so it doesn't get in the way of the bra. It just nuzzles right up to the cat. Okay. However, remember that when we actually did this last lecture. So last time we learned that this is so equal to, this is equal to sorry. Just blind there for a second. Okay, sorry. Momentum operator minus IH bar ddx. Right. So now remember, last lecture I mentioned to you that the Dirac representation of momentum is a little funky. So what it does is it turns into this, and this is our really familiar momentum operator. It's really strange because it allows the bra to jump past it. I don't see that behavior in any other operator except momentum. Momentum allows the bra to go through it. That's really weird. So it turns into a derivative and the bra goes right through it. Again, that's actually, I don't see any other thing do something like that other than momentum. So just note that's a weird one. Okay. And this is equal to, okay. So therefore, let me do some rearranging. Dx of this inner product is equal to p prime over h bar divided p prime over above minus ih bar, but I can put the I on top and eat the minus sign, and I like to do that. I don't like minus signs. Okay, so there's that. And it's the same thing. Okay. Now, if I gave you this, what would you do? Can you solve for f of x? Okay, let me point out, the derivative of a function is equal to itself. That's mostly what you want to take home from that. What function is equal to its own derivative?
E to the
E. E to the x, the derivative is e to the x. Obviously, the x has an IP over h bar. Right. Right? Derivative of that with respect to x is IP h bar e to the I. Yeah. Cool. Okay, so this is the same thing. Exact same thing. So, remember, what we're trying to solve is xp. Again, dash, I know dashes keep showing up and it's weird, but it's what drives me crazy about the book. But regardless, there's some constant, by the way, and I'll explain the constant. It's actually, I'm using the letter n as a normalization constant, because what happens is, this is all about transforming wave functions from space to momentum or backward, momentum to space, they still need to be normalized. So what you can't let this thing do, you can't let this mess up the normalization. So I'm going to keep a constant because I have a feeling that the normalization may not be preserved. So I'm going to, so there you go. Okay, now remember that this thing's job is to, again, don't worry about the dashes, it's just arbitrary label making. This thing right there, now I can take a momentum wave function and turn it to a space, and in space to momentum, you just add a minus sign there, by the way, to go backward, and I'll do some examples. So again, this isn't some arbitrary thing. This is how momentum maps onto position, and the way position maps onto momentum just means that's a complex conjugate, right? If you flip an inner product, it's just its own complex conjugate, and so you can see that you just pick up a minus sign there. And this allows you to go from momentum to position. Position to momentum just means there's one minus sign there. It's the translation from one to the other. Okay, now the thing is, when you're translating these suckers, again, you see me going from momentum to position. Like, okay, here's a point on momentum space. What's the corresponding point in position? You're going to integrate the momentum wave function times this, but we can't let the normalization go to pot. So to do that, we're going to feed this into an expression that's normalized and solve for n. So that's the big picture there. And again, I cannot emphasize enough, I am always translating position operators into momentum space and back and forth. I do it all the time. I'm going to show you why at the end of class, but you're going to learn how to do this too. And anyway, okay, so what is n? In case you, in your notes, you forget what the heck it is I'm doing. To do that, again, I'm going to give myself a question that I know the answer to. And that's, I hope you remember this. This is a direct delta function. This is a direct delta function. There we go. When you see that, just write that down. Don't have to think about it. Okay, now to solve this, I need to get momentum in here. I need to get this inside of there, inside of this. And of course, the way you put things inside of things is to resolve an identity. And again, you can break. You can, you've got to get kind of an intuitive sense where you can shove these number ones inside of expressions. Okay, so there's that. Okay, this is that. I guess the x has a little dash on it for some stupid reason. Okay, there's this. Okay, so the p doesn't have a dash, but the x does because I just use that type of notation. This is the complex conjugate of that. Let me just make sure that I'm not. Yeah, this is the complex conjugate of that. Okay. So then, again, I need to be really careful. I can't assume that we're always running into complex numbers, so I can't assume that this is complex. Okay. Again, I've got to make sure my notation is right. So it's IP. Okay, but the x does not have a dash. Okay, so there we go. Oh, minus, because it's complex conjugate. Okay. Direct delta function, minus x. Like I say, the dashes don't mean anything, but you got to be careful. You got to make sure you don't mess them up. Okay, any number times its complex conjugate is the absolute value squared. Not too bad. And the rest of this is e to the I p x dash minus x over h bar. Oops. I need to write that bigger, don't I? I know we've got plenty of people watching from home. X dash minus x Okay, crazy thing. Homework 1. Why did I have you do what was not a terribly hard problem with Fourier transforms of delta functions? Why did I do that? Because of this. I knew 2 months before that this day would come. That's why that problem was on there. So let's get rid of the n squared. And the rest of it is the definition of a delta function. 2 pi, okay, the h bar is a newcomer, so I can tell you that it ends up showing up in this part here. X prime minus x. Okay. So there you go. Now, I have to admit, when I was looking at my notes, I'm like, wait a minute, what the hell do I do from here? And look at this, right? So the delta function is equal to the delta function, and that means that, so this is actually, it turned from more of a math into a logic. Well, not really, but the absolute value of the normalization has to be 1 over 2 pi h bar. This has to kill off that because the delta function has to equal to the delta function. And we usually, at this point, you know that n could be, it could be minus the square root of 2 pi h bar. But we just decide to make it positive. It'll never matter. Constants, you know, they never matter because every observable, whenever I'm turning my space to momentum or my momentum to space, cool, then I'm going to do an operator, and then I'm going to do an absolute value. So if there's a minus sign here, it wouldn't matter. It never matters because all observables, the only thing that you should be doing quantum mechanics for is to get observables. If there's minus signs or i's, they'll always eat each other up. They get eaten up in the absolute values that are always necessary when we do these calculations. Yeah, oh yeah, so here. So, take-home message is, I'll put a little dash, because that's what your book has. Okay, again, these are little translations. These little deals tell you how to translate from one representation to the other. One reason that actually these dashes are helpful is if you're coding this into a computer, and I will have you do that at the end of class, you know, December. The dash actually is a nice bookkeeping thing for the way the program is written, so that's actually why I think they have dashes there. It's actually when you program this, you actually, it helps you keep track of what the heck is what if there's a little dash. And you'll see what I mean when you program it yourself. Anyway, there you go. Really forward, backward Fourier transform is all they are. Therefore, oh God, I'm sorry, let me do this here. Okay, I promised you I would tell you how to do this. Let's figure out how we write a momentum wave function in terms of the space wave function. It's this. Should have given myself a little room there. Yeah, there you go. That is a Fourier transform. I love Fourier transforms. They're my favorite thing in the world. I spend so much time doing Fourier transforms with MATLAB, and again, I will have to do that as well. And if any of you, I would, you know, I know that I really professionally should be teaching you Python, but I don't know Python, I know MATLAB, and I sent you all that little packet, my real half-ass, about 60-page very easy textbook on MATLAB, and I gave you some, there's practical things in there like error analysis. But at the end, I show you a data smoothing method involving Fourier transforms. So I've given you some MATLAB code. It's the end of that little packet I sent. Real quick, I got 2 minutes. Let me just show you one thing. And don't get lost about what I'm trying to do here. I got confused when I was reading my own notes. I've already written this down. And I guess I have a dash there. I don't remember if I had a dash before. Okay, so remember that momentum is minus IH bar derivative, and it allows a bra to just kind of slip past it as a result. It's just the funkiest thing in Dirac notation. The funkiest rule thing that happens is this. The rest of it actually kind of makes sense the more you do with it. But now, what I want to know is what's this. I want to turn the tables and figure out what, right? I want to be able to do everything, but instead of with position, which I'm incredibly, I'm totally fine with position and wave functions, but now I want to do momentum wave functions. But I might want to know where that momentum wave function is in real space. So so what's the position operator if I'm in momentum land? Okay, so what you do is here, let's do with this. I'm going to resolve an identity. Here's the other product. Alpha. Okay. Now what I'm going to do is I'm going to use the fact that X is an operator. Yeah, I put a hat on it. I'm just freaked out there. X is I should have had. Sorry, what have I done? One of the reasons that we have little dashes on here, I needed to do X dash because it helps you keep track of things. Okay, so X being Hermitian means that it's its own adjoint, and so I'm going to have it operate on the bra. Now remember, only adjoints of operators can operate on bras, but Hermitian operators, which are operators of things that are real, and position is a real thing, I know space exists, means that I can do this. Eigenvalue. The reason I want a dash is that when I write the eigenvalue, I want it to be clear that, that's what that is. So that's a number. That's 5, right? 5 nanometers. Okay. Now I've got this deal, and we just talked about how to deal with that. 1 over 2 pi h bar. E to the e prime, I guess it gets an x or an x, gets an x. So again, all of this is this. Now this is really funky. Okay, you're going to want to put some note in your notes here. This derivation doesn't make sense. It's a practical thing. This is, oh God, I'm sorry, I know I'm out of time. E to the blah, blah, blah is this. It's IH bar derivative with respect to P prime of E to the I. Okay, again, this IH derivative of this is equal to that. I know I'm hurrying, I know I got to finish this up. This is basically it. Then what? So now you notice that this is this is another step that's, again, a little funky. What I'm going to do is I'm going to take the derivative outside the integral, and I'm not totally comfortable with that. I know that that's considered like somewhat controversial, but we can do that. And now I recognize this as H bar D dP. All of this, of course, is the momentum representation of, yeah, so remember, this transforms this to the P representation. Sorry, I really you're late. Okay, my point being that the X operator is IH bar DDP, and the position operator is minus IH bar DDX. It's kind of cool. They're really similar. That's what this proof does. I don't really, I know I'm rushing, you may have, your head may have spin a bit, especially with this step here. And I'm not sure about how you take derivatives outside of intervals. That's really funky to me. But the point is that hopefully you're unbelievably okay, familiar with momentum operators, and then there's position operator. They're all very similar.